Hello everyone, and welcome to our video on equations of lines and planes. So, in two dimensions, we know that a line can fully be described by its slope and a point on the line. But likewise, a line in three dimensions is determined by a point and its direction. So how do we deal with that? Well, for a given line, we're going to let v be a vector parallel to that line, L, and p be an arbitrary point on L, and p naught, with the coordinates x naught, y naught, and z naught, be a known point on the line. So let's take a look at this little model here. So this black line here is the line L. And what we're trying to see is how can we describe all of the points on this line? Well, consider this vector here in red. We're calling that A. That's this red vector A. And you can imagine if you went R naught and then you went in the direction of A, you can hit any point here along the line. And if you were going in a negative direction of A, you could hit any point here. So the idea is this. You've got a vector V, which is parallel to A. So that's our vector at the origin, our standard vector. And what we're saying here is that if you take R naught plus the vector V, that gets you to this point over here. So R naught plus the vector V gets you to this point on the line. Now, we want this vector v to be arbitrary in the sense that we want to be able to get to anywhere on the line. So we know that this arbitrary point, x, y, z here, can be reached by taking r naught plus a. But a and v are parallel vectors, so we can always replace vector a with t times the vector v. So maybe this v isn't as long as vector a is here, so we want to reach this point, so we multiply this vector v by, say, 1.5, whatever it is, and that gets us out to this point here. So in other words, all we're saying is the resultant vector r in green here that takes you to a point on the line, you can always get that vector by adding r naught, the yellow vector, and some t times v, t times the vector v. So you take r naught, and then you go t times v, and it takes you to whatever point on the line you're trying to get to. So this is what we call a vector equation for L. So that's when we describe the line L in terms of its relationship between vectors. So we've got our initial vector to a fixed point, and then we're adding t times the direction vector v here. And the result is the vector that takes us to the point x, y, z that we're concerned with. So if we write this more explicitly, our vector equation becomes the following. So v is our direction vector, that's a, b, c. tv would be ta, tb, tc. Our position for our arbitrary point vector is x, y, z. And our position for our fixed point is x naught, y naught, z naught. So if we take and we add r naught plus tv, we end up with x naught plus ta, y naught plus tb, and z naught plus tc. So that brings us to the following definition. For a given line L with vector v, a, b, c, parallel to the line L, let P, x, y, z, be an arbitrary point on L, and P naught, x naught, y naught, z naught, be a known point on the line. Then R and R naught are the position vectors of P and P naught, and we can follow the following are called the parametric equations of the line L. So x equals x naught plus ta, y equals y naught plus tb, and z equals z naught plus tc. So anytime you're asked for the parametric equations of the line, you're just asked to express each of these coordinate equations separately. Okay, so example 1, find a vector equation, parametric equations, and two more points for the line through the point 6, -5, 2, and parallel to the vector 1, 3, negative 2, 3. So in other words, this vector here is our direction vector, and this is our P naught. So we need an R naught vector, and that's just the vector that takes us to that point. And again, our general vector should be R equals R naught plus T times the vector V. So if you think about this, this actually looks exactly like we think of a line in 2 dimensions, right? Like this V here is effectively our slope. You could think of it like that. It's our direction vector. So this is slope times the variable plus your point, your initial vector. So it's very similar to like y equals mx plus b form. It's not identical, but definitely very similar. Okay, so now let's go ahead and just take the information we have and plug it into this vector equation. So we get x, y, z, our arbitrary point, equals r naught plus t times v. So if I'm just asking for the vector equation form, this is a totally fine answer. However, if we're asking for the parametric equations, we would need to first combine these together. So that would give us 6 plus t minus 5 plus 3t, so t times 3 here, and 2 plus negative 2/3 times t. And so our parametric equations would be x equals 6 plus t, y equals negative 5 plus t, or plus 3t, and z equals 2 minus 2/3 t. Okay, so now if we want to find 2 more points for the line, we can just pick some t values that don't correspond to our initial vector here, right? So not t equals 0. So how about we just go for t equals 1? And what do we get there? Well, if we plug that in to our parametric equations, we get 7, negative 8, or sorry, that's negative 2, negative 5 plus 3. And then that's going to be 2 minus 2/3, so that should be 4/3. And if we plugged in t equals, let's say, 2, we get 8, positive 1, and 2/3. All right, and that's it. We're all done with that example. Okay, so let's go ahead and move on to a definition. So we were referring to this before, but let's just formally lay it out. If a vector v is equal to ABC and is used to describe the direction of a line L, then A, B, and C are called the direction numbers of L. All right, and another definition, we call these the symmetric equations of L. So if A, B, and C are all non-zero, then t can be eliminated from the parametric equations. We call the result the symmetric equations of L. And they look like this: x minus x naught over a equals y minus y naught over b, and equals z minus z naught over c. Let's just see why that works real quick. It's pretty straightforward. We already know that x is equal to x naught plus t times a, and y equals y naught plus t times b, and z equals z naught plus t times c. So if I solve each of these for t, what do I get? Well, here I get t equals x minus x naught divided by a. Here I get t equals y minus y naught divided by b. And here we get t equals z minus z naught divided by c. So as you can see, since we can solve each of these for t individually, then all three of these expressions must be equal to one another, and therefore they have a symmetry of them. And that's why we call this the symmetric equations of L. Okay, so let's move on. Example 2, find the parametric and symmetric equations of the line that passes through points A, 3, 5, negative 2, and B, 3, 1, 2. At what point does this line intersect the xz plane? Well, the first thing we're going to need is a vector, right? So we need a vector parallel to the line, and if we have these 2 points here, and we want a vector parallel to the line, well, then we can just take the vector AB. So what vector is generated between those points? And that's just going to be B minus A. So 3 minus 3 is 0. 1 minus 5 is negative 4. And 2 minus negative 2 is 4. Okay, and if we use this point A as our initial point here, then we would have an initial vector. So this would be our V. And our R naught would be the vector that leads to this point. So 3, 5, negative 2. And again, R equals R naught plus T times V. So this is 3, 5, negative 2 plus T times 0, negative 4, 4. And so here we get 3 plus T times 0, so that's just 3. 5 plus T times negative 4, so that's 5 minus 4T. And here we've got negative 2 plus 4 times T. So that leads us to the following parametric equations. Okay, now we've got our parametric equations. So we'd like to find symmetric equations, but actually there's a little bit of an issue here. So if you notice, the requirement for having these symmetric equations is that A, B, and C are all non-zero. So that's not really the case here. A is 0, so that's kind of no good. But we can still express a parametric or a symmetric relationship between y and z. So technically we would still be eliminating the parameter. It would just be the only symmetric equations we can describe are the ones relating y and z together. So what do we get? So we get t equals y minus 5 over negative 4, and t equals z plus 2 over 4. And so our symmetric equations are going to look like that. So I'm actually going to take this negative and put it up top, so it'd be 5 minus y over 4 equals z plus 2 over 4. Okay. now the final question here is, at what point does this line intersect the xz plane? So that could seem a little tricky, so let's just think about that real quick. It's actually not too complicated. So if we're talking about the xz plane, that's this plane here. So in other words, that's the plane where y equals 0. So we're just going to let y equal 0. And what do we get? Well, if y equals 0, that must mean we get 5/4 here in our symmetric equation. So that implies 5/4 equals z plus 2/4. If I cancel out the 4's and subtract the 2, I get z equals 3. So our point must be x is 3, y is 0, and z is 3. And there we go. Okay, so just a little fact here. R of t can always be expressed, so this is the vector r of t, as 1 minus t times r naught, the vector r naught, plus t times r1. So that's the vector between r naught and r1 for t from 0 to 1. So anytime you have two vectors that lead to two different points, you can always find the vector equation between them, the vector equation for the line between them, using this equation. That'll give you the segment from 0 to 1 specifically. Now this should make some sense. So the vector between these two things would be r1 minus r naught. So if we just think about our regular formula, right? R equals the initial position vector plus t times r1 minus r naught. How can we rearrange that? Well, we can pull r naught, we can distribute this t to r naught and get minus t r naught plus t r1. And then I can factor r naught out and I get 1 minus t r naught plus t r1. So this fact comes directly from our regular line equation, but in this case, the vector that we're considering is the vector result between these two vectors from subtracting them, right? So that's the only difference here. But this is a good shortcut if you've got 2 points and you want to find a vector line equation for them. This can be one of the ways you find it a little quicker, which is pretty similar to what we did here, right? We actually used this form specifically in what we did, or I should say the first form specifically. Right, we just actually subtracted those points to find the vector between them and went from there. Okay, so determine whether the lines L1 and L2 are parallel, skew, or intersecting. Well, they would be parallel if their direction vectors were scalar multiples of one another. That's the first thing to consider. So skew would mean that these lines are not intersecting and they're not parallel at all. So you might have like one line going here, and one line maybe is going like into the screen that way, and these two never intersect. So that would be skew. And intersecting would mean that you could find some point at which the 3 coordinates are the same. So to do that, you would first have to if you wanted to show that something was intersecting, you would first have to take your points and remove your parameter. So find your symmetric equations. And then once you find your symmetric equations, you'll want to say solve for one x value and find the corresponding y and z value, and then check those corresponding y and z values on the other side. So you'd have to take your two x values, set them equal from each line, solve for some shared x value, and then see if you get the same y and z value. But we're going to start with this parallel case, and if we want to check if it's parallel, all we need to see is the vector for our first line equal to some scalar multiple of the vector over the second. So in other words, they have the same direction, but maybe the vectors aren't the same length. Well, let's check. So v1 here is going to be negative 12, 9, and negative 3. And v2 is going to be 8, negative 6, and 2. Now, if these are scalar multiples of one another, then when I divide each individual term, I should get the same number. So if I take negative 12 over 8, what do I get? I get negative 3 halves. If I take 9 divided by negative 6, I get negative 3 halves. And if I take negative 3 divided by negative 2, well, that's just negative 3 halves. So in this case, each coordinate is a scalar multiple, the same scalar multiple of the other coordinate. So these are absolutely parallel. All right, let's go ahead and move on and talk about planes. So planes are a little more involved here, but they're not too bad. So a plane is described by a point in the plane, x naught, y naught, z naught, and a vector n that is orthogonal to the plane. We call n a normal vector. So how do we figure out the equation of a plane? Well, if we let x, y, z be an arbitrary point in the plane, and r naught and r be the position vectors of p naught and p, then the vector between those 2 points is p naught p, which is the same as the r minus r naught. But what do we know? Well, if the normal vector is orthogonal or perpendicular to the plane, then that means it's let's try that again. Then that means it's orthogonal or perpendicular to every vector in the plane. So if we take a look here, right, we've got this normal vector here in our model. So it's perpendicular to the plane. But that means if you draw any other vector in this plane, right, any other arrows along this plane, it's going to be at a right angle to those vectors as well. So that means that their dot product has to be 0, right? We saw that in our section on the dot product. So if we know the dot product of those things is 0, that's going to let us set up an equation for our plane. Now, equivalently, you could express your vector equation for the plane as n dot r equals n dot r naught. But we're actually going to work mostly from this first one, n dot r minus r naught equals 0. So, definition, the scalar equation of the plane. Given a normal vector, n equals abc, position vectors r equal to x, y, z, and r naught equal to x naught, y naught, z naught for arbitrary point p and fixed point p naught, respectively, the plane defined by these vectors has scalar equation a times x minus x naught plus b times y minus y naught plus c times x z minus z naught equals 0. So that's literally just the same thing we had written here. Okay, for some reason it's, there we go, come on. So that's what we had here, right? When I dot the normal vector with r minus r naught, so what do we get? We get each coordinate multiplied. So this is a times the x minus x naught. It's the first coordinate. Plus b times y minus y naught plus c times z minus z naught. So this is our equation for the plane. Let's go ahead and apply this information. We want to find an equation of the plane through the point 2, 0, 1 and perpendicular to the line x equals 3t, y equals 2 minus t, and z equals 3 plus 4t. Okay, so we actually have all the information we need here if we just consider the following. So if the plane is perpendicular to this line, then that means that the direction vector associated with this line is a normal vector. So if we look here, this vector is actually the normal vector for the plane because by definition it's perpendicular to the plane. So that's going to be your 3, -1, 4 here. Okay, and our position vector just corresponds to our point here, which is 2, 0, 1. What we want is n dotted with r minus r naught to be equal to 0. So that just means 3 times x minus 2 plus, in this case actually it's minus 1 for the second coordinate of our normal vector, times y minus 0 plus 4 times z minus 1, all equals 0. And I can rewrite this slightly and just make this negative y, but we'll leave the rest in standard form. Okay, that's it for that example. So let's go ahead and move on. So fact, the form ax plus by plus cz plus d equals 0 is called a linear equation in x, y, and z. That's because each term is a linear expression, where a, b, and c is the normal vector for a plane expressed in this form. So to be clear, this equation is the equation of a plane, and that should make sense because if we multiplied out our constants here, we could group all the resulting constants together in this one group, which is d in this form of the equation. Okay, so let's take a look at this question, example 5. Find an equation of the plane through the origin and the points 2, -4, 6, and 5, 1, 3. Okay, so we've got 2 points, and the equation also passes through the origin. So here's the origin. It's going to be 0, 0, 0. And I'm not going to draw these points particularly accurately, but it's going to look something like, you've got this vector here. This is going to be, let's call it P1. And this is going to be P2. Actually, this makes more sense for P2 where I drew that. And so P1 would be like kind of this way. Doesn't have to be perfect. We're only really drawing this to understand what we're doing. So you have these 2 vectors here. And what do we want from these 2 vectors? Well, we want the plane that these 2 vectors lie in But that means we need to find an orthogonal vector. So we have a point. Actually, we have the origin. So that's about as easy of a point as we could possibly ask for. And then on top of that, we need a direction vector, but it's got to be an orthogonal vector. So how are we going to deal with finding that orthogonal vector? Well, we can just take the cross product, right? So the cross product between any two vectors is going to give us what we want. So let's call this vector R1 and this vector R2. And if we calculate the cross product of these two vectors, that's going to give us something that's orthogonal and therefore a normal vector to the plane. So first we have to write out what these vectors look like. Well, that's pretty simple. Since each vector is going from the origin out to the point, those are just the direction vectors. So 2, -4, 6. And 5, 1, 3. So if I want to take the cross product here, so my normal vector is going to be the cross product of these two vectors. So what do we get? We get the cross product of these four terms, or the determinant, I should say, of these four terms, -4, 6, 1, 3, times I, minus the determinant of these four, 2, 5, 6, and 3, times j, plus 2, 5, -4, and 1, times k. So we get -4 times 3 minus 6 times 1, I, minus 2 times 3 minus 6 times 5, j, plus 2 times 1 minus -4 times 5, k. It's -12 minus 6, that's -18i. And this is 6 minus 30, so that's going to be -24, but we make that negative again, so that's positive 24j. And for k here, what do we have? We've got 2 plus 20, so it's going to be plus 22k. So if we think back to our regular equation for our plane, ax minus x naught plus by minus y naught plus c minus z naught equals 0. Then x naught, y naught, and z naught can all be 0, 0, and 0 since this plane passes through the origin. So using our direction numbers here from our normal vector, we get -18x plus 24y plus 22z equals 0. Okay, so let's take a look at the following fact. Two planes are parallel if their normal vectors are parallel. For instance, the planes x plus 2y minus 3z equals 4 and 2x plus 4y minus 6z equals 3 are parallel because their normal vectors are 1, 2, -3, and 2, 4, -6, which are scalar multiples of one another. So as we've seen, that means those two things go in the same direction and hence are parallel. Now, if two planes are not parallel, then they must intersect in a straight line, and the angle between the two planes is defined as the acute angle between their normal vectors. So let's take a look at this diagram or this model. We've got two planes here. They're not parallel, so they're intersecting. And this angle, if you look at this angle between their two vectors, is the same angle that you see here, this acute angle where these two planes intersect. It's a little hard to line things up in a way that makes it totally clear, but hopefully that makes sense here. So in other words, if we knew what the angle between these two normal vectors were, we would know what the angle between the two planes were. The acute angle, not the large angle, right? Okay, so let's go ahead and move on to this next example. Determine whether these planes are parallel, perpendicular, or neither. So first, let's just write out what their normal vectors look like. So if we want to know if they're perpendicular or if they are parallel, we can check the dot products or cross products, right? So we know that the cross product, the magnitude of the cross product gives us the magnitude of each vector multiplied times sine of theta, and the dot product gives us the magnitude of each vector times cosine of theta. And so we know that those tell us we can use that information about theta to determine if something is perpendicular or parallel. So I'm just going to start here by checking the dot product, see what we get. Usually I'll start with the dot product just because it's a lot quicker to calculate. So you get 2 times 1 plus negative 3 times 6 plus 4 times 4. That's going to be 2 minus 18 plus 16, which is 0. So these are perpendicular. Now, if that had not been 0, I would have checked the cross product. And then if that had not been 0, I would have been able to say, hey, these are neither. And then you can calculate the angle between them with either of your theorems about the dot product or the cross product. Okay, so example 7 here. Let's go ahead and dig into this one. Find a formula for the distance d from a point P1 to the plane ax plus by plus cz plus d equals 0. So this is a pretty tough question, I think. We got to really work on visualizing this appropriately to make it make sense. So we're going to draw a picture here. So this here is my plane. And what we're going to have here is a point not on the plane. I'm going to call that P1, X, Y, Z, X1, Y1, Z1. And it's going to have a normal line straight down to the plane. We'll call this like Q. But Q's not really going to help us find this. Well, first of all, let's just consider, we know that this plane has a vector, a normal vector here, and we can consider the normal unit vector. So I'm going to call this n sub u, right? So there's some normal unit vector with length 1 here. All right, and now I know I should be able to find some relationship between this point and any arbitrary point on the plane that will let me find this distance. So what I really want is this distance here, right? That's what I'm trying to find. So let's consider another point, though, P naught on the plane. So X naught, Y naught, Z naught. Then we should be able to draw some sort of vector between P1 and P naught. I'm going to call this V. Okay, so what does V look like? Well, V is just going to be X1 minus X naught y1 minus y naught. And z1 minus z naught. Okay, so now what am I actually looking for here? Well, okay. Well, let's get a little bit more information before I do that. So bear with me. So we also have this normal vector, which we're going to say has direction ABC. And therefore, the normal vector for this plane, the unit normal vector will be ABC divided by its magnitude, which is a squared plus b squared plus c squared. So the normal vector would be ABC, but our unit normal vector is just that divided by its magnitude. So having this have magnitude 1 is going to let us make sense of the next key step here. So what I want to figure out is what is the length of D here. But if you think about this, you can imagine that you project V, you're making a projection down, if you kind of turn your head to the right, onto this red line from V. And that means that D, the length of D here, is actually the component of V along PQ here, or the normal vector, the normal unit vector. So this is the component along the normal vector of V. But we actually just want the length of that thing, so we take the absolute value. Okay, so all that is to say is that what I'm really trying to find here is the component of this arbitrary vector from a point on the plane to P1 along the normal vector that leads to this P1, right? So if I can find that, then I'm in pretty good shape. And we know that the component can be found with the following formula. So since we're looking at magnitude here, I just want the magnitude of nu dot v divided by the magnitude of nu. But since we made this a normal unit vector, we actually know this magnitude is 1, so that makes things a little bit easier. And this just becomes the dot product, the magnitude of the dot product of ABC divided by its magnitude. With V Okay, so this gets a little messy here, but let's work it out. So this here is just dividing by a constant, so we know with the dot product we can do that constant in any order, so I can just leave that constant underneath and just dot these vectors above. And so this becomes A, x1 minus x naught, plus B, y1 minus y naught, plus C times z1 minus z naught, over the square root and we're still taking the absolute value here. Okay, so what are we going to do here? Well, if we distribute A, B, and C, we get the following: A x1 plus B y1 plus C z1, and then I'll get the negative of each of the other terms. So negative, I'll pull out in front, A x naught plus B y naught plus C z naught. And here I only put the absolute value up top because we know the square root has to be positive. And here we're at the key thing. All right, so we actually know that for any point on the plane, this equation has to be satisfied. So this is kind of the tricky part. So what does that tell me? That tells me that if x, y, and z were the specific point, x naught, y naught, z naught, then we should get that a x naught, I'll write that over here, a x naught plus b y naught plus c z naught should be equal to negative d if I moved that d across. So this should be negative d, and if I add that negative, I'll end up with a positive d. So this becomes ax1 plus by1 plus cz1 plus d. Take the absolute value and divide it by the magnitude of your normal vector. And that's it. So this is our distance formula for the distance between a point x1, y1, z1, and the plane when given in this form. Alrighty, so let's move on to this, which is going to be our last example, I believe. Yeah, that should be our last example. Find the distance between the parallel planes 10x plus 2y minus 2z equals 5 and 5x plus y minus z equals 1. Now, this seems actually a lot trickier than it is. We sort of did most of the work already in the previous problem. So let's say we've got two planes which are parallel. Since they're parallel, that means if I take any point and drop its perpendicular down to here, I'm going to always get the same distance. That's what it means for these things to be parallel. So that means I can just pick a point on one of my planes. Let's call this one P1. And this one we'll call P2. So I'm going to pick a point on plane P1. And how am I going to do that? Well, I'm just going to plug in some values for x and y and solve for z. And let's pick some easy values. Why make it difficult? How about x is 0, y is 0? And then that's going to make z, so negative 2z has to be equal to 5 then. So z has to be equal to negative 5 halves. So now the question of finding the distance of these two planes is the same as the question of finding the distance from a point on this plane to its perpendicular, the perpendicular distance, I should say, to the other plane. And that means we can just go ahead and rely on this formula. So this distance here is going to be the absolute value of a, b, which is 1, c, which is 1. So that's going to be 5 times x1, which is 0, plus 1 times y1, which is 0, plus negative 5 halves times 1 times negative 1. Let's try that again. Negative 1, that's my c, times negative 5 halves. Plus, we also need d here, but keep in mind, this equation is not in the right form here. So we got to rewrite that as 5x plus y minus z minus 1 equals 0. So this is my d. So I should use capital D for distance here to avoid some confusion. So plus d should be plus a negative 1. All divided by the square root of that normal vector. So 5, 1, and negative 1 are the appropriate coordinates there. So 5 plus 1 squared plus negative 1 squared. Okay, so up top that gives me 5 halves minus 1. So that's 3 halves. Take the absolute value, it's still positive. Divided by the square root of, this is going to be 25 plus 7, or plus 2 more. So 25 plus 2 is 27. And we could rewrite this a little as 3 over 2 root 27. Now, 27, though, is 9 times 3, right? So we can actually rewrite this further. 3 over 2 times the square root of 9 times the square root of 3. And square root of 9 is 3, so that cancels, and this becomes 1 over 2 root 3. All right, so that's it. And that's it for this whole section, so thank you for watching.